This effort is led by a two-person team. While small in size, it has achieved outcomes typically associated with much larger organizations. The reason is not scale, but architectural continuity, depth of expertise, and sustained execution. The foundational mathematics, the architectural design of EAI/NBI, and its initial operational applications have all been developed end-to-end within this team, without fragmentation, handoffs, or loss of intent. This has enabled faster convergence, higher conceptual coherence, and direct translation from theory to implementation, results that large, distributed teams often struggle to achieve. Horacio Yuche Lasada is the principal architect and originator of embryonic artificial intelligence, EAI, and non-biological intelligence, NBI. With more than 3 decades of sustained research in advanced mathematics, number theory, tensor calculus, and systems programming, he established the embryonic algebra and reconstructive operators that define the architecture itself. Horacio provides the foundational mathematical vision, formal correctness, and architectural continuity required to ensure that EAI/NBI remains stable, non-incremental, and technically sound as it moves from research into implementation. Carlos Alberto Lievano Silva provides the complementary capability required to operationalize the architecture. Trained as an odontologist and experienced as a healthcare leader and systems-oriented technologist, he brings deep expertise in organizational governance, applied artificial intelligence, and real-world deployment of automated decision systems. Carlos ensures that EAI/NBI concepts are implementable, governed, auditable, and aligned with operational constraints, particularly in defense-relevant domains such as autonomous systems and operational health. Together, this team combines origin-level architectural knowledge with operational execution capability, significantly reducing transition risk and enabling a direct path from proven applicability to controlled prototyping and validation. This continuity is a key enabler for advancing EAI/NBI toward a minimum viable platform under DARPA's high-risk, high-reward research and prototyping frameworks.
Today's artificial intelligence systems perform well in data-rich, well-connected environments, but they show fundamental limitations when applied to strategic systems, critical infrastructure, and military command and control. These systems rely on large-scale statistical training, continuous data availability, and brute force computational scaling, which results in high energy consumption, limited predictability, and fragility under degraded or adversarial conditions. Across strategic, operational, and tactical edges, command and control systems must operate with constrained power, intermittent connectivity, and strict requirements for trust, auditability, and control. Current AI architectures struggle in these environments because decision logic is implicit, embedded in opaque parameter spaces, and difficult to govern or adapt without retraining. As a result, progress in AI remains largely incremental: more data, more parameters, more compute, without fundamentally improving resilience, efficiency, or effectiveness where it matters most. ERI's Topic Area 3 calls for advanced technologies that address these gaps, requiring a shift toward architectures where intelligence and decision-making are explicitly governed rather than statistically emergent. This solution introduces non-biological intelligence, or NBI, implemented through embryonic artificial intelligence. EAI provides a new architectural foundation for intelligent systems operating under extreme constraints. Unlike contemporary AI, NBI uses compact, reversible embryonic algebraic structures instead of brute force scaling. These structures enable exact reconstruction of cognitive states and deterministic decision logic without retraining. EAI-NBI defines intelligence as a mathematically governed process rather than an emergent statistical artifact. This ensures systems remain stable and predictable across strategic and tactical environments, even under pressure. The impact is non-incremental. It replaces the underlying paradigm by which intelligence is represented. Nations gain resilient autonomous operation and integrated defensive cognition currently unattainable with conventional AI. Compact intelligence allows for orders of magnitude improvements in efficiency and sovereign control over cognitive assets. It serves as a strategic multiplier for defense, space operations, and critical infrastructure worldwide. Currently, at TRL 3 to 4, the core mathematical formalism and architectural principles are fully defined. Early computational constructs support progression toward TRL 5 through focused prototyping and evaluation. Strategic value lies in moving beyond today's AI limits to achieve resilient, governable intelligence. It is the foundation for future strategic systems where trust, efficiency, and sovereignty are decisive. To be clear, this work is not speculative. The team already has the mathematical and computational solvency required to demonstrate the functional validity of embryonic artificial intelligence and non-biological intelligence. What is proposed is a structured path to verification, prototyping, and transition. This architecture is directly applicable to the cognitive core of integrated defense systems, such as defense domes operating under saturation, and to autonomous strategic systems in space, where latency, isolation, and energy constraints make conventional AI unreliable. In these domains, the ability to govern intelligence deterministically, reduce swap-C, and scale capability in a controlled manner represents a decisive strategic advantage. Nations that develop and adopt this class of intelligence gain resilience, efficiency, and cognitive sovereignty that cannot be matched by systems dependent on brute force training and exponential compute. This difference is not incremental, it defines the next level of strategic capability. For reviewers and stakeholders seeking deeper technical clarity, a dedicated AI-based technical agent trained by the developers is available to explain concepts. This submission represents the first concrete step toward a minimum viable cognitive architecture for resilient strategic systems.